Okay, we are recording. So let's get started with a few short announcements. So I finished grading exam 3. Most students did pretty well. I think the big thing again was just showing your work. There was a lot of instances of people just saying I plugged into MATLAB and got an answer. I'm like that doesn't tell me really that you understand what happened. You just typed numbers in a computer and numbers fell out. Like that's not really showing a whole lot of understanding. And I wasn't asking for too much. Like even if you at least said, plugging into equations 5.3 in the textbook, that it was at least, something to go on. Because that's especially dangerous, because if you get something wrong, I have no idea what you were thinking or why it didn't work, right? You said I plugged into MATLAB and I got wrong numbers. Like I have nothing to work with there in terms of grading or understanding, especially. So be very mindful of that on these exams here. So speaking of exams, so I was thinking instead of having an exam 4, we'll just have the final. So we have 3 main exams that you've all taken, and then there'll be a final now. So if you did well on the first 3 exams, you are completely set. You don't necessarily have to take the final if you don't want to. But I was thinking for the final exam, there will be something like 4 questions, 1 from exam 1, 1 from exam 2, 1 from exam 3, and then something from this last section here that we're going over, right? So it'll be 4 big kind of problem groups. And so the grade you get on the final will replace the lowest grade, if it's better, assuming it'll replace your lowest grade on any of the 3 exams. So that's the idea. So if you did really good on the 3 exams, you can just kind of skip the final and hang out and do the last homework assignment. And if you bombed one of the exams, which I don't think anyone's really bombed per se, but there were a few C's in the class. So if you really want to bring up your grade that way, this will be your chance. So that's what I'm thinking will make the most sense for the final exam there. Let's see here. So speaking of which, I've got the schedule here. It was only last night I realized I didn't even actually know when the final exam is going to be. So I had to ask the department secretary, I think it's Hannah. So according to the online website, our final exam is going to be Tuesday, the 10th of December from 10:30 to 12:30. So let me just type that in. So final is Tuesday, December 10th. And it's 10:30 a.m. through 12:30 p.m. So I just put that in the chat window there. So there's that. Then also, if you're in the 6,000 level, remember you're going to have to do some kind of research report. So I'm in the middle of just typing up an official assignment for that, and it's only going to be for the 6,000 level students. So if you're in the 5,000 level, you're completely set on that. You don't have to worry about it. 6,000 level, you got to put that together. So
I have a question about the report.
Yeah.
So in the master's or graduate seminar, we also have to do a report.
Yeah.
It's a little bit more intense than this one. Can we kind of do the same report twice? Like, you know what I mean? Like
if it's microwave engineering related.
Yeah.
Honestly, if you want to double dip like that, I mean, I don't know. Is there? I feel like that should be okay. I mean, you got enough crap on your plate as it is. If it's the same work, just
I think it's okay as long as it's okay with both professors.
Yeah.
And Professor Blair said use something from another class. Don't go out of your way to.
Oh yeah.
Yeah, like because you have so much other things going on. Like, don't try to create something brand new from scratch. So.
Yeah, I'm okay with that. If Steve says he's okay with that too, because the graduate seminar class is supposed to be a light workload anyway, not too much. So I'm okay with that if it's going to satisfy both of those. It's the same assignment just with a different class title on it, basically. So as long as you fulfill the some sort of microwave engineering related thing, I don't really care. As long as it's your work, right? You're not plagiarizing, you're not copying, you're just it's the same work being assigned for 2 different classes, so I guess no big deal there. I'm putting together kind of an assignment on Canvas, and just remember the idea is, find some original research paper out there, read through it, and show. Oh, sorry, was there a question?
Oh, sorry, I kind of just got on 3 minutes ago. You mentioned final is on December 10th. What about exam 4?
There is no exam 4.
Oh, okay.
I originally thought we should do like 4 exams and a final, but now I'm kind of looking at the schedule and I was like, it just doesn't make a whole lot of sense to do that. So 3 exams and a final. The final will just replace, assuming you do better, it'll be higher of the final or your lower. Sorry, the final will be used to replace your lowest exam score, assuming your final score is greater than your exam score.
So is final optional, or?
If you did well on all the midterms, then yeah.
Okay, cool.
Or you can just accept your grade as a C, and go from there. That's okay too, right?
And does final still have like 4 parts, and we can just select the part we want to take, like each replace one?
So I was just saying, there'll be like 4 big sections on the final, 4 sort of problem sets like we do. 1 from just exam 1, 1 from exam 2, 1 from exam 3, and then 1 from the last section in this class.
Okay, cool. Thanks.
And I don't want it to be tricky or anything, so I'll probably do something relatively straightforward, like pluck out one of the problems from the previous exams, just rephrase some of the parameters a bit, and then just kind of re-ask something very, very similar, right? So I'm not going to be tricky or try and throw new problems at you there, just something to that effect, right?
I have a quick question.
Yeah.
Isn't December 10th a Thursday, not a Tuesday?
Oh, is it? I think you might be right. I might have, I just had that. You might be right. You're right. Oh, you're right. It is a Thursday, not a Tuesday. Excuse me. I must have miscopied that from the schedule online. So yes, Thursday. There you go. So we're probably gonna have 1 more homework assignment, and that'll basically be due on the 4th of December is what I'm thinking here. So just kind of looking at our schedule here. Let me do a quick little screen share. So this is the Excel spreadsheet with all of our class schedule on it. So right now we are here. We just learned about the Wilkinson divider. And after talking with Dr. First, the bare minimum, she wants to see the quadrature hybrid coupler, and then the coupled line coupler. And then after that, we just kind of have 3 lectures to fill. So she was interested in doing at least a few special topics. So stuff that isn't in the textbook, but that's also kind of practically useful and interesting. So there's probably some manuscripts that I'll post that you'll want to read over, and I'll maybe do some short lectures on that. So something about grounding in microwave circuits, maybe something on microwave resonators, and then maybe I'll throw in something with mode matching for kicks and giggles like that. And then we'll maybe do some exam review on the last day for the final. So if you don't intend to take the final, you can just take that day off and be done. And if you do want to take the final, then you can stick around and we'll go over some problems there. All right. So that is how I'm seeing the last few days of the semester. So we're going to definitely wind down the intensity a bit. We're going to talk about a lot of interesting, practically useful manifestations of microwave circuits. But yeah, just 1 more homework assignment kind of encompassing those last little bits of stuff. So I'm kind of slowly putting together a homework assignment as we go through the material to see what makes sense. Yeah, and let's make it due the last day of class. Okay, so any major questions there? I think that's everything I've got on the announcements here. Number 9. There we go. All right, so yeah, no more labs, and then we're good to go. So I uploaded a little practice problem. Where is that? I go to quizzes. So here's our attendance quiz for the day. So be sure to stick around. We'll be doing some attendance stuff as along the way. Where is that? In-class practice, November. I know I just uploaded this thing. There you are. Okay, Wednesday, November 8th. So here, let me share my screen again. Boop, there we go. So we learned all about Wilkinson power dividers. So the question is, how would you design an equal split Wilkinson power divider using microstrip? Okay. So let's just kind of walk through that right now, because this is going to be essentially one of your homework problems, is this same sort of question, right? Just something very straightforward. You have microstrip using the parameters of the board you have. How would you make a microstrip Wilkinson divider? Hypothetically, like this would have been a good lab. So think of this as like the series, the theory section to what would have been lab 6 if we had a lab 6. Where the heck are, there we are. So let's take a look here. So I'm going to, where's my overhead camera here? There you are. So I'm going to pin the video here. So the book kind of gives this nice little illustration here of how an actual power divider would look in practice if you were to make this out of your microstrip. So you have a little thin strip here, say it'll be 50 ohms. So that's your 3.2 millimeter coming in. Then you have to kind of split it off. And you notice how the split here for a higher impedance has to be slightly thinner. So I'm kind of impressed they caught on that little distinction. And then to get the lower impedance, it's a slightly thicker strip. So you can see here, this would be like 50 ohms. This would be something like 70-ish ohms. So a smidge thinner, and then it thickens up back to 50 ohms again. And then you would just slap a resistor across it right here. I was almost thinking about whether or not it'd be worth trying to make this in real time here, because theoretically the analysis is pretty straightforward. But I'm just thinking, like, I've got a board here and I've got a soldering iron and we have a half hour to kill here. So what if we tried to actually make one right now? How would that work? So we'll go through the theory section. If we get really motivated, I can fire up the soldering iron and see if we can actually make something like that. We could just measure it with our nano VNA and see what happens. Or at the very least, I could get through half of it and then we'll look at it Friday and see how that goes. All right. So the question was, so we're with microstrip. So the first thing we need to know is, what is the thickness of our microstrip going to be? So if I have, say, a 50 ohm line, let me pull up the, oh, I was supposed to say 50 ohms. I gave the center frequency. I forgot to do the actual impedances of everything there. So we're going to assume 50 ohms because that's how everything is. So we also know our center frequency is going to be 2.4 gigahertz because that's everyone's cell phones is around there. And we also know using microstrip that at least our microstrip, this is not a generally true thing, but it's true for our particular boards, that our propagation velocity was about 0.55 times the speed of light. So that implies some wavelength is the velocity divided by the frequency. And we also know, oops, we're going to need a resistor. Sorry, I got too much stuff over here. There's going to be a resistor R. So that little bridge resistor is just going to be 2 times V naught. So that's a 100 ohm resistor is going to have to bridge that. And we know 50 ohms corresponded to something like 3.2 millimeter, 3.1, 3.2, right? I think that was about it. So then we also know the little bridge here. So we have square root of 2 times Z naught. What is that? So I've got MATLAB up here, so I'm going to do a little quick calculation. So square root of 2 times 50 is, yeah, 70.7 ohms. So then the question is, what width do I need for my strip to get that? It's gonna be somewhere like 2.5-ish millimeters. It's gonna be really a little bit thinner. Somewhere between 2.5 to 3 and so we'll look that up in a second. And then we also know that this length, this little branch here, has to be a quarter wavelength. So assuming the velocity of propagation doesn't change significantly, we know that lambda over 4 is going to be, well, we gotta calculate this stuff. So frequency is 2.4 gigahertz. Velocity of propagation. So here, let's just write a quick little script file that does all this stuff. So I'm going to open up MATLAB real fast, and then we'll go to, are we lecture 29 right now?
Yes.
Okay, I'm in the right directory here. There we go. So let's do a little screen share. There we go. There we go. Okay, so let's just find model parameters here. So we know our frequency was 2.4. Velocity of propagation was 0.55. Characteristic impedance was 50 ohms. What do we want to call ZX, I suppose, for the little branching guys? We'll just say square root of 2 times Z naught. And we need a wavelength, so that's VP over F naught. So then I'm just going to say L, I guess, is the length of the branch, was just lambda over 4. So these are all the basic parameters here. So you want to comment this center frequency, which is in hertz. Phase velocity, that's meters per second. Characteristic impedance. Let's see, this is, do they call it, do they give a name to that branch thing? I guess I'll just call it the branch impedance. Wavelength. And call it the branch length, I suppose. Yeah, I went through the derivation. I didn't pay too much attention to what they call little bits and pieces of it.
They didn't call it anything. That frustrated me as well.
Yeah, the book like shows you the schematic, but like you have to name this stuff as you go through, that sort of thing. So we'll look at that. So L, that's going to be 1.7 centimeters here. So let's stop sharing. In fact, if I'm going to make one of these, I feel like it'll be fun to make one of these. So I'm going to change the frequency. 2.4 is kind of, it's outside of the range of our nano VNA. So I'm going to make it just 1 gigahertz instead. Let's make a little modification there. So now we can actually like test it out when I put the thing together. Okay, so let's see. We're looking here. So I'm going to cross that out. I'm going to put 1 gigahertz. Now the nano VNA can actually play with it. And then lambda, here we go. So lambda became 16.5 centimeters. And so lambda over 4 is, there we go, about 4.12 centimeters. There we go. So the final question is, what is the width here going to have to be in order to make that little guy be the right impedance? So now we got to go back to, what was it, lab 4, I think, where we did, yeah, the microstrip. So I'm just going to run that real quick and we'll do another screen share. So you remember this graph here? Nope, that was our phase velocity. So we can assume that's not going to change too much. And where the heck was that? There we go. So this was I got all this goofy annotation all over that. So I'm going to remove some of that stuff. Sorry, because I originally had it set up where it'd run a simulation. And I was kind of comparing against that. All right, so remember this. We had characteristic impedance versus our width. And we had about 50 ohms. And then we need to figure out, ooh, that's going to be really thin. I wonder if that's going to even be doable with my bare hands. So let's do a quick little check here. So I'm going to, so there's my 50 ohms there. I'm going to do another one with square root of 2 times that. There you go. So you see there's our 2 little intersection points. Ooh, that's going to be tough. So you see to get our 70-ish ohms, I'm going to need 1.5 millimeters. Ugh. I wonder if I can do that with my bare hands. That's going to be tiny. But there you go. So we know that the width here had to be about 3-ish millimeters. So actually it's not quite. Yeah. And then this guy is, we'll zoom back up. So we'll say 1.5 millimeters there, 1.5. Okay. So there you go. That's essentially a Wilkinson power divider in a nutshell, is those parameters. So we'll go back here. So this is everything you need to know. You know that this length will have to be 4 centimeters, and these are the widths here. So what you would have is something, let's see if I can kind of draw this to scale. Well, you'll have a width coming in like that. So I'll call that maybe W1 and W2. So that's about 3 millimeters, 3-ish. I think I updated it with my actual dielectric constant. So I'm going to put about 3 there. And then you have to branch out. So you do something kind of like this. Like that. So you'd have these little branches. And I wonder how much of an impact it has on that, where exactly that sort of those overlaps are. But usually this stuff is pretty forgiving if you're making it out of this stuff. And then you have another bit coming out basically like that, I guess. So the book kind of shows it drawn more like this. So it would look kind of like that again. Although I'm totally not drawing this to scale, sorry. So this would be my thin here, my 1.5 millimeter. So yeah, I did not draw that very well at all. So let's just kind of do that. So ignore some of these lines here. Like that. Yeah, I kind of garbled that a bit. And then this kind of just goes on like that. And then what you would need is a big fat resistor here. Just sort of soldering like that. So that'd be a 100 ohm resistor, kind of like that. So hypothetically, if I were to make this right now out of microstrip, I should get a pretty decent result. So this would be about 4.12 centimeters like that. So then there's a 4.12 centimeters like that. Okay. And that's basically it. Now you have a Wilkinson power divider. And if you wanted to make this thing, you'd have to terminate this with 50 ohms here. So you'd put, say, a 50 ohm resistor here. And then what you would do is you'd feed your nano VNA into this port, and you would excite a signal, and then you could measure your transmittance out to the other end here. So let's grab this guy here. So you'd have your nano VNA. You notice you have, we were measuring reflection coefficients with this port, but you can actually measure a transmission coefficient by just feeding from one into the other. So this would be your channel 0, and then your channel 1 would come out here. And that's it. And then you can just measure both ports. So you terminate this one with, say, 50 ohms. So you put your little 50 ohm load there and then measure this. And then you could do a little flip-flop, or you could send the signal the opposite direction and see what happens. And there you go. So you can see how pretty straightforward it is to make a Wilkinson divider here. And in reality, you wouldn't necessarily use big, thick feed-through resistors. You'd have like little chip resistors for this sort of thing as well. Oh, and that reminds me of one other thing. So actually, Corey was kind enough to donate some images from L3 of some of their microwave networks here. So what I think I'll do is I'll try and build one of these tomorrow and see how it goes. because making that 1.5 centimeter is going to be a real challenge. But we'll see how that goes. But we also, let me see if I can find those images. There we go. So am I still screen share? So I'm going to do a screen share. There we go. Something like that. So that is to give you a sense of scale for some of the very itty bitty devices that go into some of these microwave networks. You can see how this is like nice and crisply cut on these strips here. So I'm having a hunch this was probably, I think they use etching to make that something like that, some kind of photolithography. I'm pretty sure they also have little milling machines that'll just grind out the copper as well. I know you can get some of those. So Corey, if you want to chime in of anything, if I'm misexplaining any of this. So here's another great example. I think you said this was a Chebyshev filter?
Yeah, 5-segment, 5 gigahertz low pass filter.
Interesting. So these, you can see, you can't even tell what these are. These are probably inductors and capacitors here, or what?
Yep. If you look carefully, the ones that are running the length of the transmission line, those are inductors, and you can tell that it's a little white plastic wishbone, and you can even see because it's made from a little wire wrapped around that wishbone. And that makes it really difficult. Yep. You can kind of see the horizontal lines on it on the one closest to the pen, the pen head.
This guy here.
Yep, you can kind of see how it wants to make horizontal lines. And so that's actual 3 wrappings of a wire around a plastic dog bone.
Interesting. Okay. So there's like a little copper wire. Is that like that little wire there? That's like a copper wire just in a little coil around this?
And that makes those things a bugger to solder, because when you're doing it, if you accidentally bump it with your iron and one side's still soldered, you'll actually end up pulling that wire off of the dog bone. And then you've just invalidated its performance.
So these were hand soldered then?
Yeah, and it's difficult, but it's not as hard as you think. This filter I soldered, and it was very gross in its performance when I measured it, but that's good enough for me to send it down to another building and have a professional solder it.
So this was the frequency response I think you gave here.
Yep.
So this is actually measured on a network analyzer?
Correct.
Okay, so you notice we're getting up to, starts at 100 megahertz and stops at 20 gigahertz here. So it looks like somewhere around here, we can read the markers. So right there is about 3 gigahertz, 5 gigahertz. So, so the brown, so that's an S11. So that's the reflection coefficient, it looks like. So it's kind of like a low pass filter, it looks like. Yep. You can see the ripples there. So if it was a binomial filter, that would probably be a much more flat response. But you said it was a Chebyshev, right?
Correct.
So if I understand correctly, one of the advantages of a Chebyshev filter is you're sacrificing a little bit of your insertion loss in exchange for kind of better bandwidth, it looks like, or better stability. So that's what that rippling is going on there. So it's not going down to like minus infinity. It's just sort of hovering there around 20 to 30 dB, which is fine because usually 20 dB is considered a pretty good result. And then all of a sudden it just boom, right up at around 5-ish to 6-ish gigahertz here. It shoots up to a very high value here. So you're getting, it's a low pass filter there. And then you see this blue looks like the transmission, S21. And yeah, you see how it's, so what, does that make sense to see 20 dB here? Or has this got some sort of offset?
So that's regretfully on these devices, the blue, if you look up at the blue where it says S21, see how it says negative 20 dB?
Yeah, so
it's
there's an offset.
20 dB offset off of the caret you see on the screen.
Yeah, because you can see the number here where it's indicated, it says 0 dB here. So it's just offset there. So the 0 is pushed up.
Yeah, and that moved up because this screen image, if you look at it, the filter does have a re-entry above 18 gigahertz, and I wanted to encapsulate that in the screen photo.
Interesting.
Screenshot.
So yeah, we're getting a bunch of transmission through here, and all of a sudden just shoots down to basically nothing. You're way down on the noise floor. And then, but you notice as you go higher and higher in frequency, it really wants to creep back up again, doesn't it? And that's just because those little devices just have all those parasitics in them that start really manifesting as you go higher and higher in frequency. You probably also can't even really treat it as a circuit anymore as you get up to 20 gigahertz, because now your wavelength's going to be like, what, a millimeter at that point? So there's a lot of just full field stuff happening at that point there. So that's pretty interesting as well. So yeah, I don't really have any chip capacitor. Well, I have some little chip capacitors, nothing on this kind of scale though. But that's to give you, that's a great little demo to see just like how you can make this stuff in practice. And you can get up to 5 or 6 gigahertz. So when the book said 1 gigahertz, I think we decided that's probably a bit dated, because this is like the 4th edition. Yeah, 4th edition of Posar's book here. So let's just, for fun, take a look at the inside cover and see when the first edition came out. Let's see, 1998. So maybe 20 years ago, it made sense that 1 gigahertz was the best you could really do with lumped elements. And 20 years have gone by, and that paragraph hasn't really changed, but maybe the state of the art has a little bit.
They're making even smaller surface mount devices than that as well, because that's an 0201, and they're now making 00501s. So the length
00501, okay.
Yep. So the length of those ones is half. The length is the width of what you're seeing on an 02.
Okay.
And I'm sure some manufacturers are about ready to come up with components that are meeting RF standards as well. And I'm sure when that higher frequency matching, higher frequency filters, and these things are way cheaper and easier to implement than buying somebody else's filter.
Yeah. So I'm assuming when you soldered this, you did you just use hand tools, or you had to at least have like a microscope or something, right?
That does. So I know Professor Blair has a stereo microscope.
Yeah.
And so it's an actual full-on microscope that has 2 probes, one for each eye, and you set it up just perfectly. So when you're looking in the microscope, you still have your depth perception.
Yeah.
If you don't set it up right and you only see it with one eye, you'll be pushing everything around with your iron, because depth perception is critical. And then I just had 2 irons, and their tips are needle point enough to actually poke yourself. Because you have to fit that iron in between the gap between those. And as you can see, it doesn't look pretty because I'm not that good at it.
I was gonna say it looked pretty good. There's a couple of them are a little crooked there, but that's still pretty good for doing with your bare hands. So you're saying you had just the needle, the iron in your bare hands, and you just kind of soldered there. You didn't even have any special kind of microscopic soldering instruments?
When I first saw this, I thought this was absolutely crazy, but you'll be surprised. You sit down, and with a little bit of practice, it's not as hard as you think it is.
Yeah. So I remember doing my very first internship was at a company called Volterra, and they just made switch mode power supplies. And there was this technician who could just babble for hours about all the magical world of soldering. So he taught me a lot of how to do some of that small soldering. So you have the stereo microscope, and there's all this special hand technique to keep your hands from jittering as you try and solder stuff down. But I never quite got that small, at least not with hand soldering. I would assume you start maybe using heat guns or something at that level, but no, that's pretty impressive there, especially because that's the head of a pen, it looks like.
Yes.
Okay.
So that the trace width for that 50 ohm line is 16 thousandths of an inch, so 16 mils.
Do you know what that is in millimeters?
This whole metric standard thing is frustrating.
You can just Google that right now.
Yeah.
You'd say 16 mil to millimeter is, that's 0.4 millimeters? Is that right? And that's 50 ohms?
16. That sounds a little small.
Yeah, that can't be a half a millimeter there, I think.
the.
Also, you also sent me the data sheet. Here's the actual specs for the chip conductors. So you see their Q
Yeah,
factor.
so those.
Oh, there's a
are
nice little.
O201s.
Yeah.
So whatever width an O201 is, that's the same as that trace.
The O201, is that on this data
Yeah.
sheet? By the way, so is that kind of what the picture looks like? So there's this little little wire sort of wrapped around there.
Yep.
And you're soldering to the tips. And you can't really, oh, you can kind of barely make that out if you zoom way in. You can almost sort of, so it looks like there's a wire and a wire and a wire. So 3 turns on that little guy. It's probably all sort of encased in some epoxy or something, I imagine. So yeah, so it's just a little itty bitty teensy weensy wire with some contacts that you solder to. So does it say here? So C, 0.45 millimeters, is that really? That's what it says here.
Yep, 0.5 millimeter.
Whew, that's pretty impressive there. And you said that's a 50 ohm line?
Yep.
So that would imply a couple of things. It's possible that you see how there's copper here around it? That might also, that'll have an effect depending on how close it is to the impedance. Is there a ground plane underneath, or is this the ground plane around it here?
There's a ground plane underneath.
Okay. Looks like this is also ground.
Yep. And I think there's a magic balance in between everything, because this is pretty industry standard. The Rogers material that's printed on is of a specific effective dielectric that allows you to use a trace width that is equal that of an O201.
Okay.
And then also makes it so that coplanar microstrip guide that you have on the side is also the span of an O201 for the very purpose of making stuff like this. Because everything looks like it's just matching up perfectly. It's because that dielectric, and that's like these industry standards that everybody comes up with, and I know very little about it, and I'm learning as I'm going.
So you have, so if you fix this distance here and you put a ground plane on it, that'll affect the characteristic impedance. We also know that changing the dielectric will have an effect as well. So for example, I've got the model right here. So if I were to say increase the dielectric constant, you saw how that lowered the impedance of everything, which would imply you need much smaller traces to get that same 50 ohms, right? So that's one thing you do. And then adding those ground planes around will probably also lower the impedance as well. In fact, yeah, because it should increase the capacitance, and it's the square root of L over C. So that would lower the impedance, which means you would need a smaller trace to bring it back up. Okay, all my intuition driving there. So there you go. So that's a nice, fun little exercise. Okay, but that's pretty much all I had today. So I wanted to say thanks for sharing that, because that's a nice insight into some of this stuff happening in real life. And in particular, I kind of feel bad that we didn't quite get to do Chebyshev filters, because we did the binomial, and right there in the textbook is Chebyshev filters, which is exactly what you said this is, right?
Yep.
We just didn't do it out of stepped impedances. It looks like you did it out of lumped elements with like a ladder, it looks like. So if I look at this again, because it looks like you made that out of just a ladder of inductors and capacitors, not out of stepped changes in characteristic impedance on the line. Is that right? Because mathematically, the result is still kind of the same. There's just different ways to approach it. So that's pretty cool. Okay.
Yeah. On this one, my mentor just gave me a solver, and he said, punch in the numbers and how many segments you want, and it'll spit back the values at you. So I dutifully did that, and it met my design requirements. But yeah, that's interesting. I'll have to look at that in the textbook.
Oh yeah, because the textbook, we do it, because you saw the binomial filter, we did little steps in the characteristic impedance. So you'd go from like, 3 millimeter to 3.2 to 3.4, or it would step small if you want to go high impedance, that sort of thing, or it'd step bigger if you wanted to go lower impedance. So this is made out of lumped elements, inductors and capacitors. But mathematically, it still has that same sort of equal ripple behavior. So it's a Chebyshev filter, a low pass filter there. All right. Yeah, so that's pretty much all I've got today. I think what I will try and do if I have time is make the divider on my board here and solder it up just to see how it behaves. See if I can get an actual 1.5 millimeter trace without ripping it to shreds, and then we'll solder it and see how it behaves. Okay. So other than that, so thanks for coming out. I think the class is going to kind of wind down over the next few lectures because we're kind of through all the nasty nitty gritty theoretical stuff, and we're just getting into some nice practical devices at this point. Okay. So yeah, thank you for thank you for joining.